Welcome to the fifth video in the kinematics section. This one's on non-constant acceleration. And what we've done to date using the Suvat equations are to do with constant acceleration. Those equations themselves are derived on the assumption that acceleration is constant, and I'll kind of demonstrate that to you in a few moments. But the main thing, I suppose, to note with non-constant acceleration is that you do need some knowledge of differentiation and integration. So this video assumes that you've got some knowledge of that, certainly using the power rule. If you haven't, then all is not lost, because if you dive off into my short video on differentiation and integration for kinematics, then it will give you really more or less what you need in order to be able to do this without having to become a calculus expert. So what's this all about then? All right, so first thing we need to note is when we're thinking about velocity, what is velocity? It's the rate of change of distance stroke displacement with time. In calculus terms, we kind of denote it like this. Okay, and acceleration is the rate of change of velocity with time, similar notation. And when we talk about rate of change, rates of change mean gradient. Fine if you're working with straight lines, pretty straightforward, take the rise over the run. But say we've got something a little bit more complicated. Say this is a velocity time graph down here, and this is telling us that the velocity is this function. It's a sort of polynomial function in t, and we could calculate the velocity at any particular point in time just simply by plugging the time in, t equals 2 or whatever it is, into this function, and that will give us our velocity. But if we're going back to this statement, the acceleration is rate of change of velocity with time. The rate of change is the gradient, isn't it? Now, what's the gradient on this curve? Well, it depends. It depends on what the value of t is. So the gradient function, and therefore the acceleration function, is going to be a function of t. So we're going to expect to see t in there. It won't be a constant, of course, which is why it's non-constant acceleration. It will be variable and will vary on t. So if this is the velocity function, our acceleration function is given by the derivative dv dt of that function, and that's going to be this function here. So it will vary over time. And you might say, of course, therefore, if we've got if we've got the velocity, we can find the acceleration function. If we've got the acceleration function, and we need to use acceleration in order to get back to velocity. And in fact, the same true as the relationship between velocity and displacement. So velocity is the rate of change of displacement with time. So if we've got the displacement function, we can find the velocity function. We've got the velocity function through differentiation. If we've got the velocity function, we can find the displacement function by integration. And so we can kind of summarize it in this little diagram here. If we want to go from displacement function to velocity function, then we find the derivative, the gradient function. And then from velocity function to acceleration function, same again. If we want to come the other way, then we're having to integrate as we go this way. So we can pretty well move between these functions and derive one from the other. The only thing we have to remember is, of course, when we're integrating, because we're doing the reverse process to differentiation, then we're going to end up with a constant of integration. Now we can usually resolve for that constant of integration in the problems that we're given, because we will be given a boundary condition. So in other words, when t equals 0, v equals 0, or v equals 3, or something like that. So and that'll become clearer when I follow the examples through. Okay, so this is what we need to do in order to derive displacement, velocity, or acceleration from each other. Now, it's just worth noting, I think, that this where the Suvat equations actually come from, because we start off with the assumption that acceleration is constant. So on the basis of what I've just said, if we want the velocity, we have to to find the integral of a with respect to t, this being a constant. Then what we're doing is we're just following the power rule, and we get at plus our constant of integration. But then if we apply this boundary rule, in other words, when t equals 0, the starting time, then v equals u. I use that because that's what we use for our initial velocity very often. And we substitute that in this equation, v equals at plus c, t equals 0, v equals u. Then we find that c equals u. So v equals at plus u, and which we would write as v equals u plus at if we wanted it to be in the form of our velocity Suvat equation. So that's basically where it comes from. And then if we go a step further and say, well, okay, we've got the velocity, let's go and find the displacement function, then we just integrate it again. So we're integrating that velocity function, which of course is u plus at. And this is how we get ut plus half at squared, but of course plus our constant of integration. Now, normally in linear kinematics, we tend to assume that the starting displacement is 0. We kind of don't necessarily assume that in vectors, which we'll come to in another video, but usually that is the assumption that we make. And so if we assume that when t equals 0, s equals 0, that gives us c equals 0. This constant of integration drops out, and we get our displacement kinematic Suvat equation. So so that's really what non-constant acceleration is all about. And so best thing to do, I think, is just move on and do a couple of examples. So this one's fairly straightforward. Particle moves in a straight line, and at a time t, it has velocity v, where v equals this function. So if we wanted the velocity at any given point in time, t equals 2, then we could just substitute it in here and find the velocity. And this, of course, would be some kind of curve. It's got t squared in it, so we'd expect it to be positive. So we'd expect it to be a sort of a pudding basin shape. Okay. So in order to find the expression for the acceleration of the particle at time t, as in part A1, we just differentiate it, and that gives us 6t minus 12. That's just applying the power rule to the velocity function to get the acceleration function. So that's pretty straightforward. When t equals 2, show that the acceleration of the particle is 0. So then we're just substituting t equals 2 into our acceleration function, and that's going to give us 6 times 2 minus 12, which is equal to 0. So that's part 2, pretty straightforward. Now, when t equals 0, the particle is at the origin. So this is, you can spot this straight away as being a boundary condition, and the particle is at the origin. That means that's a sort of bit of text, which means displacement equals 0. So this is saying when t equals 0, s equals 0. Okay, we'll come back to that. Find an expression for the displacement of the particle from the origin at time t. Right. So in our little sort of league table of A, V, and S, what we need in order to derive the displacement is to integrate the velocity function. So which we can write like that. expand it out, substituting the velocity function in there. We've got the displacement equals this expression with respect to t, and that just comes out as s equals t cubed minus 6t squared plus 6t plus our constant of integration. But going back to our boundary condition, when t equals 0, s equals 0, what we've assumed, and we plug those into this equation, then we just get lots of zeros basically, and we end up with c equals 0. So we can knock that out of that equation, and we're just left with our specific. This is what we call a general solution. But what we've got is a specific solution which applies to the situation that when t equals 0, the particle is at the origin, as opposed to anywhere else. So so s equals t cubed minus 6t squared plus 6t is our expression for the displacement of the particle. So that's a kind of fairly straightforward one. This one is a little bit more complicated. Let's have a look. Car travels along a long straight road for 1 hour, starting from rest. After t hours, its acceleration is a kilometers per hour, where a equals this expression 180 minus 360t. Now we know this is not our normal units, kilometers and hours. We're usually meters and seconds, but the whole question is in kilometers and hours. So there's no need in this one for us to convert to anything. That's just going to add complications. So we can just keep everything in kilometers and hours. Okay, so the first question is find the speed of the car in kilometers per hour in terms of t. So so we've got its acceleration. Okay. We've got acceleration equals that. So the velocity is equal to 180 minus 360 t with respect to t, giving us this expression with our constant of integration c. And we're told that when it starts from rest. That means t equals 0, v equals 0. So we can substitute those into this equation, and that simply gives us c equals 0. And then we've got our fully formed specific equation, which here I've written down. I've actually factorized it. I've factorized 180t out of there to give us this expression here. Part B says find the range of times during which the car is breaking the speed limit. Give your answer in minutes. Okay, this is the graph here. We could draw that, stick it into Desmos or wherever, and it will look like this. Quite interesting, really, because it's got positive velocity for an hour. We're not actually interested in what happens outside that hour, but if we were, we'd actually be into negative velocity after 1 hour. But yeah, just that 1 hour period that we're actually interested in. So this second part is more about solving an inequality really than anything to do with kinematics. The car is breaking the limit if v is greater than 40. So you can see if we take the line across here at 40, it's this time period here where it's just kind of bumps over that horizontal line. So we can express that in terms of an inequality. 180t into 1 minus t, that is the velocity, is greater than 40, and then we just solve for t. Divide through by 180 gives us that. Turn it into a quadratic expression, a quadratic inequality, by expanding it and subtracting 2/9 from each side. Note though that because this t times minus t gives you minus t squared, the signs of this left-hand side have been changed, and therefore the inequality sign has been swapped over, which is all about inequalities, really. But just take note of that. And then if we solve that, without going through the details, it's just a solution of an inequality. Then we find that t is between 1/3 and 2/3. I think that looks about right, doesn't it? You know, if we take drop a line down from those 2 points where where the curve intersects, v equals 40, then it seems entirely reasonable that we get 1/3 and 2/3. So it's breaking the speed limit for that period. Okay, so that's part B. Now, part C, find the average speed of the car over the whole journey. Well, to find the average speed, we need the whole distance. Distance and displacement here are the same because we're just looking at it's the same sign. We're not changing sign throughout this hour. The velocity is positive all that time. So displacement and distance we can use interchangeably. So what we want is the total distance divided by the total time. So time is hour. So really we need to find our displacement function first of all. The displacement function, following our process, we integrate the velocity function, and we get this: s equals 90t squared minus 60t cubed plus our constant of integration. And we're also we're basically because we're measuring the displacement with respect to where we start, then this is a sort of implicit boundary condition that we get. It's t equals 0, s equals 0. That time t equals 0, the displacement is 0. And that's going to give us, and when we substitute it in here, it's going to give us c equals 0. So our specific solution is this s equals 90t squared minus 60t. And then all we need to do is find out what that distance is after 1 hour. And just substitute t equals 1 in there, and that's going to give us 90 minus 60 equals 30. So it's 30 kilometers. So we've traveled 30 kilometers in 1 hour, and therefore the average speed is 30 kilometers per hour. Okay, so that is the gist of it. So those two are sort of kind of pretty typical, I think. You know, they can get a bit more complicated than that, obviously, but really the principles are not too difficult. And if your calculus is up to scratch, then you shouldn't really have too much difficulty with those. So hopefully you found that interesting and useful, and I will see you in the next video.